This conference will now be recorded.
Today, guys, we are going to look at more like complex convolutional neural networks models and something that is super important in this area that is called transfer learning. And then we will do an example, training something using transfer learning. I take it that you are now fine with the previous concepts that we did, like convolution, max pooling, the Rulu layer, etc. I take it that it's okay for now.
Yes.
The filters,
Yes.
this 5 by 5 by 3, what it means.
Mhm.
So this is the channel, 5 by 5, this the size of the kernel, 5 by 5, this kind of thing.
The window.
Exactly, the window, and then we slide. We slide along this. So how many, just a quick question, guys. How many parameters this neuron has?
Parameters?
Yeah, how
Input?
many weights? How many weights? Yeah. It is connected to a 5 by 5 by 3 window. So how many weights does it have?
Don't know.
So each, generally in a neural network, in a neuron, each input has a weight. We multiply the weight by the input and we sum them up.
Yes.
So how many weights do we have? Very simple.
5 times 5 by 3.
By 3, exactly. So exactly 5 by 5 by 3.
3, 25 times 3.
Yeah, it's 25, 75. But we don't forget the bias, plus 1. So it's 76.
But I think Reza is the initial weight, and then after with the back propagation, this will be changed. No.
No. This neuron has this weight. The single neuron.
But after.
No, but back propagation doesn't change the number of weights. It uses more memory, but it doesn't change the number of weights. So each neuron has a fixed number of weights that it's going to learn. So the neuron, what it does, it multiplies the input by the weight, and then it does a sum. So the first input by its weight plus the second input by the weight, etc. So each input has its own weight connected to it, plus the bias, which is another weight. So here we have 76 weights for this neuron, and the same goes for other neurons. Okay. So this is one neuron or one filter. This is another neuron that is generated, and so on. So if you want to compute the number of weights per layer, we just look at how many activation, actually the filter size, and how many activation maps we have. So here we have 2. It means the total number of weights for this layer, if we have 2, it will be how many?
5
by 2.
5 by 3
by 2.
Multiply 2.
Yeah, by 2. So 76, which is 152.
Yeah.
Okay. And so on. This is how we compute the weights. There will be an exercise by the end where we are going to compute like the whole memory of a neural network, of a CNN especially. Well, if we know how to compute the number of weights for a CNN, we will be able to do it for the dense layer, for the regular neural network, because it's just like a part of the CNN. So we'll be able to do it. So an exercise here, how many filters do we have here?
6.
So we have 6. If we are using a kernel of 3 by 3 and 3 channels.
Yeah.
So how many total weights do we have here in this layer?
10 or 11. No.
It's 10. Yeah, 3 by 3 by 3. So the kernel is 3 by 3. And then we have 3 in depth, the number of channels that we are going to take from here. So a neuron is connected to a zone of 3 by 3.
Okay, so Reza, please, how we can do for knowing the number of activation maps? It's we divide
It's up to you. There is no way to know it in advance. It's very hard. You can estimate it. You can try a number. Generally, if the problem is complex, we go for high numbers. If the problem is very simple, we go for small numbers. So, for example, in the previous example that we did last time, with MNIST is considered as a simple problem. So we use like just 32, I think, in the beginning. We didn't use like high numbers for the number of filters.
Okay. For example, here in this example, if we take the window or the filter 5 by 5, it will be here 6. And if we take it 3 by 3, it will be 10.
Yeah, it will be 3 by 3 by 3, 9 plus the bias 1, it will be 10. But how many total weights? How many total weights do we have? So this is for one neuron. Here, how many neurons are there?
It's 3 by 3 by 3 by 10.
No, not by 10.
By 6.
10 is this 3 by 3 plus 1. But in total, how many do we have? We don't have 10 neurons. We have 6 neurons.
Yeah. In this case,
yeah. In this case,
but
yeah.
But no, rather, if we have a filter about 3 by 3 by 3, we will have 10 features map, I think.
No, not features map. No. This is a filter of 3 by 3 by 3. This is just one single neuron.
Yeah.
One single neuron is connected to this, and any other neuron is connected to the same. So each neuron will have 10 weights, 10 parameters connected to it. Is it fine? This neuron is connected to a window of 3 by 3.
Yes.
And in depth, it's 3. So we have here 9 dots.
Yeah.
So each dot will be connected to its weight.
Neuron. Yeah.
Exactly. It will be connected to each neuron. So how many params do we have? How many weights do we have?
3 by 3 is 9 by 3.
Yeah, 3 by 3 by?
Plus by.
Yeah, it's not 10. It's 3 by 3 by 3.
By 3 by
plus
6.
1. Exactly. Thank you, Miriam has got it right. Yeah. It's 3 by 3, 9 by 3, 27 plus 1, 28. So it's 28 weights, not 10.
Yeah.
And how many neurons do we have?
1.
I think it's 10.
6.
Why 10 neurons? It's 6 neurons. Each neuron will produce one activation map.
Is it point 6?
Excuse me. Just here, I have a question.
Yeah?
I think there is a relationship between 32 and 3. The first image, I mean the input.
No, 32 is the size of the image. We don't really care about it.
But if we divide 32 by 3, we can get 10 feature maps.
This 32 doesn't. We don't care about it with the number of feature maps. The number of feature maps, each feature map will learn a particular shape. So, for example, this feature map, maybe it is learning this shape. This feature map, maybe it is learning this shape.
Okay, so we can't know the exact number of feature maps.
You fix it in the beginning. You don't know what shapes do you need in the beginning. So you fix a number and you see if it works or not.
Reza?
Yeah?
May I ask about features? I was thinking that features we do calculate it. We compute it. About features.
What do you mean by computing a feature?
Yeah, for example, maybe I need to compute features by pixel. I need to compute feature by geometry. So I need many. I don't know.
The thing that the magic, if I can say, of CNNs is that they will determine the features by themselves. It's geometry based. So by themselves, it will learn what features do we need to know to do the classification. They are automatically learned. You don't need to tell them that.
Okay, so
this is the strength.
About CNN.
Yeah,
But if I use other, for example, model like UNet, I have to calculate it.
UNet is also based on CNNs. UNet it's that is called semantic segmentation.
Yeah,
Yeah, UNet,
exactly.
no, you don't need to compute it as well. UNet is also based on CNNs. So you don't need to do that. The CNN, the neural network, will it by itself determine what features do we need to learn. This is the strength, the main thing that, because it's very hard, for example, on NAI, when we have a NAI, it's very hard to know what features do we need to learn. Maybe something that is like this, maybe something that is a direct line, like you have to decompose it into different shapes. And to do that by hand is a horrendous task. Plus, the eyes are different from one person to another. So a convolutional neural network will, automatically by itself, decompose all the eyes and see what are the best set of features that it needs to learn. So you got that concept. It's really autonomous. You don't need to tell it how to operate. So to go back to the number of weights. So when we have this neuron connected to a 3 by 3 by 3, so 3 by 3 in the size and 3 here, we have the depth, the number of channels. We don't care about this 32 and this 32. This is the size, and this neuron will slide over here. The size of this activation map will depend, of course, on the size of this, but the number of weights in this neuron will be simply the number of inputs to it. How many inputs do we have here to this neuron? Mahdiya, please tell me. How many inputs do we have to connect to this neuron at a time?
I think 10, no?
3 by, so how many inputs? We have
3
3
by
by
3 by 3.
27.
Yeah.
27, and always we have +1 for the bias. So we have 28 weights in this neuron. And how many neurons do we have to produce this activation map? These maps. How many neurons do we have?
6.
Exactly 6. So it is this multiplied by 6. So this is to know how many weights do we need to train in this layer. This is 28 by 6 to know the number of weights in this layer. And if we want to compute the number of weights on the following layer, we do the same thing. Is it okay? All of you guys? Yusuf, are you happy? Amal, are you happy?
Oh, yes, yeah.
Perfect. All of you guys, I don't need to ask you one by one, but you should, if you are not happy, please tell me. So this is how we compute the number of weights. Let's move on. So this is the first architecture, AlexNet. That CNN model, this is the third CNN model that won the famous ImageNet competition. It's a competition where different teams around the world like stack their models to compete against each other, and the best models will be placed in the leaderboard. Generally, if you are one of the best, you can get some excellent contracts or some work or some job offers, this kind of things. And I mean by excellent, like really of the chart things. So what happened here? The first CNN architecture that took part in this competition. So the error rate here was 15.3% against 26.2 for a second best. It's a really, really big margin. It's like smashing the score here. Like around 9% difference. 9% difference is really, really big. A big difference. or more, sorry, 11%. 11% difference. This is really like smashing the score. So what they used, the ReLU instead of the tan hyperbolic or the sigmoid. What's the advantage of the ReLU? What did you say last time? Or the what advantage does it have? The ReLU compared to the sigmoid.
He gave a better gradient.
Perfect.
It's faster.
It's faster and gives a better gradient. Yeah, because the gradient is better, so the steps will be more optimal to compute. We'll have better steps, so the gradient descent will converge faster. And of course, the gradient, when it propagates, it doesn't fall in the variation gradient problem. It always falls there, but it is less susceptible to it, unlike the sigmoid. It uses the dropout. What does the dropout do?
He selects different each iteration different neurons, so he creates multiple neural networks.
Exactly, it's like ensemble learning. The effect of a dropout is like ensemble learning. It's like we are training multiple neural networks and averaging them together. This is the effect of a dropout. And we saw last time when we tried the two examples, one with the dropout, the last ones, and one without. What happened? Can you remember what happened with the dropout?
Yeah, we got better accuracy.
Yeah, you remember that the score for training was stable. It wasn't going high very quickly. But at the same time, the score of testing was very close to the score of training. The accuracy of training and testing, they were very close to each other. But when we removed it, the score for training was going up very high. The score of testing was okay, but it wasn't as good as in the second case. So the dropout like kept them together. They were going to like up, like almost at the same rate. Are you happy with this, guys? Can you see that in your mind?
Yeah.
And then they use pooling layer. What does pooling layer do?
So
Reduce size.
Yes, thank you.
Reduce
Yeah, it reduces the size of this. For example, from here, we divide it by 4. If we use a max pooling of 4, so we divide it by or by 2 and by 2 from both dimensions. So the reduction will be very high. So they use this to achieve this super high score, which is very impressive. Now this is AlexNet. Then it had 62 million variables, parameters, which is quite a lot. So this is the number of features, 96. So it has 96 filters, as you can see here. They use 96 at the beginning. In the beginning, they had 11 by 11. Now we don't use 11 by 11. So we generally use very small, like kernels, a filter with a small size. Here it's 11 by 11 by 3. So can you guys, an exercise for you. I will give you 5 minutes to compute it. Can you tell me how many weights do we have here in this first layer? 5-minute exercise. Tell me how many weights this first layer has. This one. How many in total? How many weights do we have? I'm giving you 5 minutes, and we come back.
Excuse me, Rida, what we have to do?
Compute the number of weights that we will have in this first layer. How many do we have? How many this layer has in terms of total number of weights? Anyone has an answer?
No.
Is it 290,401?
I haven't computed it. Let me just quickly do it. I don't think it's that big of a number.
11 by 11, I think, by 3.
Oh, you might be right. Yeah, sorry, I didn't see this. It's 11 by 11 by 3 plus 1.
Yeah, for one.
Multiplied by
one-
96.
Yeah, is that.
That's what you did, Yusuf?
460.
No, I did the second one, 96 times 55 times 55.
No, it's not that.
The third layer.
It's the number of weights. So this neuron, one neuron, is connected to this.
459.
So let me just compute it, guys, quickly. So it's 11 by 3. Multiplied by 96. So it's almost 35.
217.
No, it's like around 35,000 almost. That's what you got?
Is it 34,944?
Yeah, exactly. Yeah, exactly. Thank you, Amal. What did you find, Miriam?
No, not that number.
It's actually 11 by 11 by 3. So this is the size
Yeah.
of the input, and that plus 1 for the bias. So this neuron is connected to this, so it has this number of parameters multiplied by the number of neurons. The number of neurons is
Yes,
just
96. Yes,
96. So we got something like around 35K.
35K. Yes.
Same here. If we want to know how many features do we have, it's 5 by 5 by 96 now. How many weights?
5 by
Yes.
5 by
5 by
96.
5.
By 96
by
plus 1
plus 1.
is
Plus 1 times 260. 56.
Times 200.
exactly. That's for the second layer. We are computing now for the second layer. Let me just compute it to make sure we are 5 by 5 by 96. This is for one neuron plus 1, 2,400 multiplied by 256. So it is now a lot bigger, more than 600,000. In this layer, it's more than 600,000. That's what you got, guys?
Yes.
And same goes in here, 3 by 3 by 256 multiplied by this, and we can compute the total number of weights. The most of the weights will be here, because here it's densely connected. For example, here it's 256 by 13 by it's all are connected. We don't have windows, so this dense layer is connected to everything. So it's no longer a small window. So it's 256 by 13 by 13 multiplied by this number to get the total number of weights here. Which makes things, but here it's a lot smaller. We need always this to be a lot smaller, so we get a small number of weights here. Otherwise, we'll have a big number. So this is how we compute the number of weights. I'm just preparing you for the section where we compute the memory and these things. Many companies ask you these questions during interviews, how to compute the weights of a CNN, the number of weights, even the number of RAM that you need.
Sorry, Rida, how can we do the weights for the last one? How can we do it?
Last one, now in the last one, it is one neuron is connected to everything. You don't have windows. So instead of, for example, 11 by 11 by 3, it will be 13 by 13 by 256. Every neuron is connected to everything.
Right.
So we do that 13 by 13 by 256 multiplied by the number of neurons, which is 496.
Okay.
4,996. So we got that. And we do the same here, same thing in here. the number of outputs. So each neuron here has one output. So, and they are all connected. So it's 4,000 output. So for each neuron here is connected to 4,000 multiplied by 4,000. So here we get the number of weights in here, because every neuron is connected to everything here. Here it's a lot simpler. It's just a multiplication to the input with the number of neurons. The input here is all of this multiplied by the number of neurons. Plus 1, of course, for the bias, which is just a plus 1. Is it okay, guys?
Just last question, I think, about that, about the number of activation map.
Here we don't have an activation map. Here it's
No. I'm
here,
talking about in the conclusion.
The number of activation maps, because every neuron will produce one activation map.
Yeah.
We call it a neuron or a filter. So every neuron will produce one. So that's the number of neurons, basically.
I mean the best choose about the number. It's experimental.
Here, yeah, it's experimental. It's very hard to know what's. These guys probably they tried different combinations of all these numbers.
Okay.
Before getting some results. And if I'm not wrong, they had a very hard time to train it. I think, if I remember, they used 2 GPUs, and they didn't have like libraries like now. So they needed to do everything by hand, which is a horrendous task.
Thanks, sir.
Is it fine, guys, for how to compute this? So it had 62 million variables, which is quite a lot if we sum them up. Next architecture, VGG. This is for VGG. So it starts with 64, a lower number of. I think it has like just 3 by 3, if I'm not mistaken. The kernel size is smaller, and like here it starts by 11 by 11. In VGG, it's just 3 by 3, and most of the time it's 3 by 3 kernels.
Sir.
Yeah.
VG 16 or 19?
Sorry. VG. Yeah. This one is probably, I don't know. 16 it just means 16 layers, and 19 means that's 19 layers. Doesn't really matter much for the course. I don't know. We have to compute it how many we have here. So we have VGG 16. We have even, I think, less. So we have VGG 16, VGG 19. Just the number of layers that we will have. So with VGG, you can see we have 2 layers of both of 64. Then a max pooling to reduce it. Then 3 layers, each of them 128. Then 4 layers, each of them 256, and so on. And after 2 layers, we put a max pooling. After 3 layers, another max pooling. After 4 layers, a max pooling, and so on. So we put layer and the max pooling. Now modern architectures, most of them, like they put 1 layer and immediately they put a max pooling. A lot of modern architectures, they don't stack like 2 layers and the max pooling. They put multiple max pooling quickly in the newer architectures. So this is the VGG. It came, I think, 1 year later, something like that. So it's very similar to it, just it has more layers and smaller filters, smaller kernels. Kernels are smaller, the VGG. So they use convolution plus ReLU, same as the AlexNet, max pooling, fully connected layer, plus ReLU, and the softmax at the end determine the result. So with VGG,
softmax we use it for classification. Is that?
Yeah, for softmax, when you have outputs, it transforms it. So here we can have any number here without the softmax.
Yeah.
So here we have 1,000 neurons at the output. So we get 1,000 outputs. Each neuron produces 1 output. When we use the softmax, it transforms this as a probability, which means that their sum will be 1.
Okay.
So if we are doing a classification, the highest probability will be the class that we want the network to classify the example into. For example, if we are trying to classify things into animals, it looks, for example, to the image of a cat. Here it's a cat. It goes here, and we get probabilities. Without the softmax, we can get different numbers, but softmax transforms it into probabilities. Their sum will be 1. So that if this is the neuron that will recognize cats, this will be a high probability, say 1.8. And we got a little bit in the others, 1.1, for example, 1.05, etc. But their sum will be always 1. The sum will be always 1 when we put the softmax at the end. Okay?
Yes, thanks.
We use it when we have like one single label to determine. It's one or the others. It's just one output. If we, for example, we have multiple labels to determine, so it can be a cat, it can be a colored image, it can be, it's like we have multiple outputs, and they can be all at the same time. For example, it can be, it's like we are, if we, for example, we try to recognize if it is a car, the color here, color, type of car. Here, all of them are like, they can be all at the same time. So we don't use a softmax because the picture can be this and this and this at the same time. It can have a color.
As capturing image.
Sorry?
Or annotation image. As annotation image.
We call it, yeah, multi-label image. So it can have multiple labels, not just one. But let's keep that for later. For now, we are just classifying by
what we use label. In this case, please, Reda?
We don't use the softmax.
What?
We put the regular sigmoid at the end of each neuron, independently. The sigmoid will produce either it's a probability that is close to 0 or 1. When it is 1, it is the case. When it is 0, it is not.
Okay.
And their sum doesn't sum up to 1 when we put the sigmoid at the end. But let's keep that for later when we try different cases. For now, let's focus on this. So what happened with VGG? It went to 92%. The previous one was 15%, which is like around 85% accuracy. This is the error rate. Then when they just put more depth, they put double convolution pooling, double convolution pooling, 3 convolutions, then a pooling, 3, and 3 dense layers to recognize. They achieved, so it was, they just, what they did is just to go deeper, mainly. They put more layers, and they achieved 92%. If you compute how many layers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and plus 3, 16, without counting the pooling layers, etc. So this is why we call it VGG 16. So we have 16 layers. Each one have its own filters, etc. The number, the feature maps, etc. Each one has its own. Now that we looked at some of the first architectures that did a revolution actually compared to the previous ones. Let's have a look at transfer learning. So normally, in your opinion, we need a lot of data to train a CNN, to train something with this number of features, of parameters, 62 million. This is a big number. You probably need big data sets for that, don't you think?
Yes.
Okay, yeah, that's true. To train it, we need a lot of data. We can always use with images data augmentation. For example, a picture that contains a cat, if we rotate it a little bit, it will still be a cat. Do you agree with me?
Mm-hmm.
Yeah, we can use this tricks for data augmentation. And we can also take advantage, this is the most important thing, of a previously trained model. With convolutional neural networks, you can take a model that you trained on a data set and apply it to another data set. Do you agree with this? Sorry?
Even if they are completely different data sets, I mean, they
yes,
learn
even if they are different, not completely, of course.
Yeah.
Even if there is some difference, and of course, what you can do, you take the model altogether, and you tweak it. You start retraining it. You keep it as it is, and what you call that fine tuning. like you train it further. You take it as it was before, and you start modifying it, not starting from the beginning, but starting from like where the model was for that previous data set, especially if they are close to each other.
Like doing an upgrade to it?
And you can call it that way. It's not really an upgrade, but like fine-tuning it. It's like you tweak it to make it better for your new example, your new data set. It was good for the previous data set, but because the two data sets are not too far from each other, because when we look at a scene, it's not like a big difference. When you look at an image that contains animals or cars, the basic shapes, this horizontal line, vertical lines, they are more or less the same.
Mm-hmm.
But you take that and you start fine-tuning it, like making it better for your other case. And this is a very strong point here. It works so well, almost like magic. It works very well in CNNs, this transfer learning. For example, AlexNet is available for free, or VGG16, or even bigger models, trained on very large data set. ImageNet, this is a huge data set. I don't know how many gigabytes or terabytes it contains of images. Trained on a very, very big data set. It is available for free if you want to download it. Trained there, it does this amazing scores, a score like that. You can take it as it is and fine-tune it for your case. For example, this is the case with transfer learning. We take VGG16, trained on ImageNet with its weight and everything ready. We remove these layers, the dense layers. These layers make a decision, because this is recognizing the shapes. This is the more we go on, the more complex the shapes we can recognize when we go in depth. Yes or no? You agree with this?
Yeah.
When we go, for example, here, if these horizontal lines or vertical lines, here it could probably be faces. Here it could be eyes. So the more in depth we go, the more complex the shapes we are being able to recognize. So each layer that is deeper, we recognize like more complex shapes. So this layer, the dense layers, we take this outputs, the complex shapes, and make a decision what it is. So what we do, we can remove this. We take this, like in here, and you add few layers of dense layers, 1 or 2 or whatever you need, and you start fine-tuning the network on all. What you can do, when you connect it to new layers, you can even freeze this. What does it mean, freeze? Freezing it. What do you think it is?
Stop learning?
Sorry?
Stop learning?
Exactly. We stop it. We don't modify it at all. We train only this, and this stays as it is. It doesn't make sense to like keep this without even modifying it and just try to make a decision here. But it works surprisingly well, even
So
when we freeze it.
We keep the basic shapes and we train only the complex.
Yes, but it is like still in 2 different data sets, but it really works surprisingly well. You get very high scores even with that. With freezing it, you can freeze it, or you can unfreeze it, not making it frozen, and you start fine-tuning. But this will not be modified a lot because it has reached a maturity level that will allow it to classify this. So we will have some small modification here in this if you don't freeze it. Sometimes you can keep these dense layers and you modify only this. You modify only this dense layer.
Okay.
Okay.
Reva,
Here it's another. Yeah.
transformer, we use the pre-trained model.
The transformer
Is
that
that
is
what you
used in NLP.
The NLP, yeah,
The transformer, you mean that one?
yeah.
Yeah, we use transfer learning for it, exactly. It is one of the first models that allow transfer learning in NLP. Before that, when we used RNNs, it was very hard to apply transfer learning. But with the transformer, we could use it very well. But it's not as good as for CNN. You need always to not to freeze everything with the transformer. You have to to fine tune it a little bit. But for CNN, you can freeze it and you still do well. Okay.
Okay.
We can also do that. We remove only one layer, and we add a custom dense layer to it. You can freeze all of this if you want things to be quicker, or you can fine tune everything. This is what we were talking about. So you can fine tune everything or freeze them. You can even freeze them. Yeah.
Can we add LSTM neurons or
of course
other
You
CNNs?
can add you can add LSTMs to this. Yeah. So we learn some sequence of images, for example.
And we can put it in the middle of two.
You want to put an LSTM like a CNN, then an LSTM, then a CNN.
Yes.
The LSTM will produce continuous outputs. Will produce a sequence. You can use a CNN for it, but it's a one-dimensional CNN. You can. It's not. I haven't seen that in practice used a lot, but you will use a one-dimensional CNN. It's like to produce new features, but I don't know if it is used that much. In theory, you can do it. There is nothing preventing you from using that architecture, but I don't know why you do that. Generally, when we do an LSTM, like a CNN, then an LSTM will recognize sequence of images, for example, and then we add a dense layer at the end that takes the sequence of encoding and produce some output. That's what we generally do. Okay. Are you happy with this? What do you do?
Yes. Thank you.
Perfect. Okay. Now, when do we freeze and when not? So when you have very little data, you don't have a lot of images, and you know that you have a model that was trained, a big model that was trained on very similar data set close to it. So you can fine tune a linear classifier on the top, fine tune only something here in here, then or even add one single neuron, or depending on the number of classes you have. But if the datasets are very different, you are in trouble. You are really in trouble because your dataset is very small and your model is too different, trained on something that is very different. So you probably need to collect more data or something like that, do some trick. If you have a lot of data, you can fine tune just few layers, like you freeze this, or you unfreeze it, or you freeze only this, for example, the beginning. You can choose how many layers you freeze. And because you have a lot of data, you can take this model and fine tune only some layers. If they are too different, you have to probably fine tune many layers. If the two data sets are too different that where the original model has been trained, you can fine tune a large number of layers. But if they are so similar, you can freeze almost all of this and add just few layers here, few reconnected layer, sometimes only one. And in other cases, you can even put an SVM or a decision tree here. That is, we haven't used that before. So you can even put something different than a neural network here, if the two datasets are very similar. Does it make sense for you guys? Does it make sense?
Yes.
Yeah, you can, if they are so similar, you can freeze it all together. And even put here a decision tree or an SVM is very good to put here to do the classification, because these layers won't learn anything. They will be frozen. So we fire the image, we get the output, and we train the SVM or whatever we want here, and it will still get us good results. Transfer learning is now the norm. It is used a lot now. But it is not really like always required. It's optional generally. It depends on how many images you have in your data set. But we use it almost all the time for different problems. Let's see other architectures and how they. So this is the ImageNet competition. So these are the winners. Yeah, every year. This is shallow. Shallow, it means it is a fully connected layer of just 3 layers: inputs, then a middle layer, a hidden layer, what we call, and the output layer. You remember this architecture that we used the first time with neural networks? Do you remember it, guys?
Yes.
All of you. This is the regular neural network, like input layer, and then a hidden layer in the middle, and then the output layer. Sorry. So
It's
we have only
machine
3 layers.
learning, not deep.
This is a regular shallow network, an MLP.
It's belong to machine learning, not deep.
Well, deep learning belongs to machine learning as well. That's terminology. Yeah, but it's not deep learning. It's not a deep learning network.
There is no.
Yeah, just one hidden layer and one output layer. That's all. So those two cases, that's what they use. That's what we call by shallow.
There is no feature extraction parts here.
Nothing. Just a regular neural network. Yeah. In the beginning, here in 2010 and 2011, these are the 2 that won the competition. This guy got an error rate of 28%, and this guy 25%. Then AlexNet came. AlexNet was the first one to win the competition. It is based on a CNN, just 8 layers, and you see the drop here. You could see like the drop between from year to year how it was. Less than 3%. Yeah, 2 point something. And here, it's considered as smashing the score here. Then another 8 layer. I don't know which one was it. It was something probably close to AlexNet. I don't know how this was trained. You can refer to their paper if there is any. Then VGG came. The VGG19 version went to 7.3%. Then we had GoogleNet. It had more layers and it had versions with insane number of layers. You can see here, 152 layers. But the winner in 2014 was a 22 layers network. We will see what they added in GoogleNet. It was a team from Google. Then these guys came. It was also considered as a more or less of a revolution, ResNet. And they dropped again from 6.7% to 3.6. The difference doesn't look so huge, but in terms of percentage, it's very big. And then you see that the difference started like to plateau. And this is a human baseline. Like this is just a guy who tried to classify ImageNet data by themselves, and they achieved an error rate of 5.1%. So you can see from here, ResNet was able to beat them. Yeah, they were. ResNet was able to beat humans. So they achieved a score of 95%, and the ResNet was like at 96.4%. And then we kept going better and better. And we have, I think, now DenseNet that is more or less state of the art. Any question, guys, here? So you could see the revolution that we had with CNNs. revolution that here we shallow, and then probably we had other models that were based on traditional machine learning, like segmentation plus feature extraction, etc. That's how we used to do things in the past, plus a classifier. Sorry guys, someone is having some echo. Can someone? Okay, nice stop. So, any question? Any? Are you fascinated at least by this? I can't hear you, Najwa. If you are talking, I can't hear you. Are you fascinated by these results? By the way, they were able to beat humans since 2015.
Yeah,
but there
and
is a catch.
short.
Yeah, and it's really one of the revolutions that we had in this field. But there is a catch there. There is a catch. It's not that it's perfect. There is a catchy thing. So this is GoogleNet. What GoogleNet did is that they added different filters, different kernel size. So here it's 1 by 1, here 3 by 3. They computed a lot and then they concatenated them. It's like you have multiple filters. So your filters here, when you have the image, and then when it goes to here, the feature map. So each neuron, so they have groups of neurons, of 4 neurons. So they have groups of 4 neurons. Each neuron have different kernel size. Here it's 1 by 1, then 3 by 3. 1 by 1 is this is the image, sorry, 3, and this is a size maybe 256 by 256. So each neuron is connected to a small portion of the image, but the portion differs. In the first group, it's 1 by 1, then 3 by 3, 5 by 5, and 1 by 1, another 1 by 1. So they have like different sizes they use, and then they can concatenate them. So the filter size, that's okay, Maria. So this will be like, they won't have the same filter size. Like each group will belong to a partition, to a group. So the filter size will be different for this group, different for this, different for this, and then they concatenate them. Sorry. So that's what we do with GoogleNet, and then we go we'll go big in depth. Is it clear, guys? It's simple. It's simple enough. Is it clear what they did with GoogleNet?
Yes, so they use a different filter and then concatenate all the
results.
features.
So exactly. So the features here, the activation map will have divided into 4 groups. So the first group will be just 1 by 1, second group 3 by 3, and then 5 by 5, and then 1 by 1. But they have like a double layer here. Well, once you feel comfortable, we will explain what this 1 by 1 means and when we put double layers, etc. But once you feel more comfortable, we will go further. So that's for Google Maps. Are you all happy, guys, with what they did? So they used a variable kernel size. Yusuf, are you happy?
Yes, yes.
Perfect. Amal, Najwa?
Yeah.
Perfect. Then we had this next revolution, which was ResNet. This was an excellent one, but I'm not going to explain it now. I think it's too much. I will give you a pause and we go for some practice. Okay, guys? So it's a 10-minute pause.
Okay.
That's fine.
Yeah, and then we will do some practice. So see you in 10 minutes.
Okay, thank you.
Thank you.
This conference will now be recorded.
So now we are going to train a classifier on this data set. So look at this data set. What is this? It is more or less, I'm not sure if it is the case, it was taken from Kaggle. So we try to detect if someone has got COVID or not from the chest scan. So these are scans, and some of them are infected and some of them are not. So here it's normal. These guys are not infected. So we have like, I don't know, a number of, well, I'm going to tell you later how many images do we have. So it's 74 items, 74 images. And this is for not normal. These are for guys with some infection. Here, this guy here. So these are the images with infections, COVID. So we have different images. So it is divided, this data set, into two parts. So this is the training, class 1 and class 2. And this is the testing. It's another folder. We organize it that way. Class 1 and class 2. So testing has got like less classes, less files. 20 items for class 1, 20 items for class 2. Here, for training, for class 1, we've got 74. For class 2, 74 as well, which is good when we have, we have this balanced data set. So the number of items per class is the same. And now we are going to try to detect if there is a chance that we can detect if someone has COVID or not, only by looking at his scan, chest scan. An expert can probably do it, a human expert. So we put that into a folder, divided into two folders, train and test, and then in each folder we have two folders for each class. So we have just two classes here. So this is just to specify the folders where we are. Image size, this is just when we want to resize the image because the size are different. Don't worry about this random seed. I will explain it later. Batch size, at each iteration, is the number of samples that we use to train. If I use more or a bigger batch size, I will have some problems because my GPU is small. So this is interesting. Keras graciously gives us this class or this function, image data generator. We give it the folder that will come later. And what it does, it produces images from the original image, but with transformations. So here we have rotation range. It takes every image and tries to rotate it randomly by a 30 degrees range, like the way, rotating it by 32 degrees between 0 and 30, randomly, with shift range, with height shift range. We also modify, like the width and the height. Shear range, I'm not sure what this is. It's another transformation. Brightness range, we change the brightness, the color, by 0.5 and 1.5, a little bit. And also what we do is flip the image horizontally and vertically, like that and like that. So we do a lot of transformation, and these transformations generally they don't modify the content. If someone has got COVID and you rotate it a little bit, he still got COVID. Do you agree with this? Guys, does it make sense for you?
Can you repeat it, Rida?
So this image data generator, what it does, it takes your original images like we had here, and what it does, it augments them. It produces new images based on them. But how? By these parameters. Rotation range, it takes in some images and randomly rotate them by 32 degrees, but between 0 and 30. When we rotate an image, it doesn't change the content. Yes, Yusuf, yes or no?
What did you say?
When you rotate an image you rotate it a little bit. If someone has got COVID, it doesn't change. You still get COVID. Has
Yes.
COVID if we rotate it a little bit.
Yeah,
Yes,
it doesn't.
it's
Yes, but
Yes.
but
same.
my question: why we rotate it?
To augment, so the data set will become bigger. That's a good question. Thank you, Yusuf. Is to make the data set bigger. It's like we have only 70 images, but if we apply this, we get a lot more images.
Why we don't use Smoot?
Smoot is not applied for images. That's a good question. Smootty, what it does, more or less, so you've got your data points like this. It is data augmentation technique, and it looks in, for example, in this zone, we have only circles. So it augments here, puts here circles, new ones. Here it sees that we have only triangles, so it augments things, but put in here triangles and augment the data set. But here we don't have really a representation an easy representation in the space. An image is very hard to represent. If we change, for example, if we change here, we change the 1 pixel a little bit, we don't know if the guy still got COVID or not. When we move it here, it's modified 1 pixel, for example, a little bit. We don't know if the guy still got COVID or not. It doesn't mean a lot, like modifying this the color of a pixel. But when we do the transformation in this, when we rotate it, all the pixels are different. Yes or no, Ali? When we rotate the image, all the pixels change.
Yes, it's.
So the point is very far, because all the pixels change. The point is very far from it, but it's still a triangle or has got COVID. So Smootty doesn't apply well in this kind for images. We use Smootty for tabular data sets.
But
Does it make sense?
But why you didn't use 19 or 180? You flip it all.
Sorry, what?
Why you didn't flip it? You didn't flip it.
Flip what?
30%. It's my.
No, it's randomly. It's randomly between 0 and 30. This is a number. 30% is fine. We keep the same information.
It's
like
not degree.
Sorry?
It's not a degree. It's
a
degree. Percentage.
It's a degree. No, it's a degree. If I'm not, it's a degree between 0 and 30, and we rotate the image randomly a little bit. Between 30 is not a big range, so we don't really lose a lot of information. Like if we rotate it by 90 degrees, maybe it's fine. So did you say something?
I thought that it's range from 0 to 36, 360.
You can do that. It's fine if you do it, if you want to do it. But you just need to make sure, for example, if your image is not a square, it's a rectangle. If you flip it by 90 degrees, you will lose the edges.
Okay.
Because the size is, for example, is different. So you have to be careful on how you rotate it.
And
so
how much picture it will generate?
It's the same number as the original, but it's different for each batch iteration. Each batch will be different. So it's 70 plus 70, it's 140 pictures, but each batch they will be different pictures.
It will be the new number, the new dataset. It will contain 140 image.
Yeah, in each iteration, when we are training the network, each iteration we get 140, the same as the original data, but all transformed using this randomly transformed. Every time they are randomly transformed.
At each epoch, it will generate new images.
Yes, new images, all of them new, but based on these transformations.
Fantastic.
It's not always the original images that we are going to use or the original transformation. Each epoch has its own set of randomly generated image based on this.
I didn't understand it. How he can generate new images while it does not call this function? Or
it does. Who told you it doesn't?
How? Show me the code.
We are going to go to. We are going to look at the
Okay.
code. Don't worry. Because in the code, in the training, in the train, in the not in the compile. Where is my thing to train? Yes, model fit generator. We gave it the train generator. This is the fit generator, and we give it the train generator. The images will come from here.
Fit function.
Sorry? What did you say? Train generator is this one. Is this one?
You don't use model .fit.
Not model.fit, no. Here we are not using model.fit because we need something that modifies the images. It's model.fit generator, not model.fit.
Now I understand.
I'm happy that you are happy.
We change the old function with the fit generation.
Yes, fit generator now it produces new images in every iteration. So that way we get different images at every epoch. So these are some modifications. So we end up with a much bigger data set, guys, than what we had. Are you happy with this? Does it make sense for you guys? Yusuf, Amal, Miriam, please. Farouk, Mahdiya, Najwa.
Yes, it's okay.
Yes, thank you.
Perfect. One thing here that we are going to use is transfer learning. So this is to generate the data, to load it and transform it. We are going to come back to process input, sorry. We'll come back to it. Then we get, we call this test.gen flow from directory, and we give it color mode, RGB, image size, 256 by 254 by 224, sorry, etc. The number of classes, one means only one neuron. One neuron can predict like two classes. One or means two here, because one is the number of neurons. So what we did here, sequential, same as last time. We did sequential, do you remember? When we built it in the network here.
Yes.
Use sequential in the beginning. Then we started putting our layers one by one. But here what we did, base model. It's not a layer based model. It is coming from here.
No.
It's coming from here.
It's our first model.
It's a model that it is actually VGG16 as it was trained and when it won the competition. It's exactly the same one. The authors made it gracefully available for free. It is a file that you can download, this one.
VGG have two dense layers into the end. You didn't stop them, no?
Two or three, I think. I'm not sure
But you
if
didn't
this
stop
version.
them here.
I don't know if this version gives me only the the CNN, the conv layers, or if it gives me everything. I'm not sure about it. I haven't checked it. I should have. So this is it. Normally, I need only the one without the dense layers. So this is it.
Please, you mean here pre-trained?
It is pre-trained.
C'est ça?
It is pre-trained. Here is the file for it. It is 56 meg big, not that big. We download it. We specify the file where it is, and then we load it. We give the file, etc., and the input shape, and we get the layer. When we call it, we get it as a layer. It's like a layer, and we add it to my network. And then what I did here, guys, flatten. It means that I'm going to flatten all of the input of the CNN, the output of the CNN, to make them, because the output of the CNN is 3D, something like that.
Yes.
It's something like that. So flatten transforms it into something like that. So each cell will become one like this. So we always need to flatten before adding the dense layer. And I just added one neuron at the end. You can see, guys, here, one single neuron, activation sigmoid. When we have one neuron, a sigmoid or a softmax is the same because it's one single, just one neuron at the end. So here we have only one neuron. And only one neuron is still because of transfer learning. One neuron is able to, we train it and we see how much we will do. Here you can see, guys, model.layers of 0. It means the first layer, which is this one. Trainable equals forced. What did I do? It's very intuitive. It's very easy to know. What did I do here?
I have to repeat the
Freezing.
time.
Exactly, freezing, yeah. We froze this.
Oh, okay.
We froze the first layer. And then we continued normally. So here, the optimizer I'm using RMS prop, if you remember it, with a learning rate of 0.001. And then we start, this is the model summary. Let's execute and see what will happen. So the model summary, it will give me the information about the model. So 148 images belonging to 2 classes, 40 for testing belonging to 2 classes as well. This is my network. This is for VGG16 model. It has 14 million parameters, or or almost 15 million parameters. Almost 15. Then a flatten. Flatten doesn't have, a dropout doesn't have. And then the dense layer. The dense layer has 20, it's just one neuron. You can see only one single neuron, it has 25,000 parameters. Total parameters, 14 million. Trainable parameters, only this. Because all of these are frozen. So what we are training, only this.
The last layer.
Yeah, exactly. One last layer comprising one single neuron. Let's train, and you will see how fast it is compared to if we did it normally. And it has like 16 layers. It's a lot bigger than the previous example that we used here in the first cases. Here it's very small. The number of layers were smaller. Here it's 16 layers, VGG16 plus one single dense layer. Let's see how fast it is. But I'm not using a lot of number of steps.
So Reda, here what we are trying to do, we are trying to use ImageNet model as it is, and after we add one layer, this layer will recognize the rotation of the images, something like this.
No, not the rotation. The rotations are the images. We have rotations or transformations. Some images don't even receive rotations, possibly, if the number is picked is 0. We are trying to recognize if the guy has got COVID or not. That's what we are trying to recognize. The rotation is just to make my dataset bigger.
What are we trying to recognize, Reda?
If the guy has got COVID or not.
A guy
or not.
COVID.
Yeah.
Okay.
Based on the images contain if it has COVID or not. The rotations, as I said, is just to augment the data. We have more. We generate more images. So let's see. It was very quick compared to last time.
But Reda, please, the VGG here use the same dataset?
No, not ImageNet dataset. It's completely different. ImageNet has got millions of images, but it still works so well.
It's general image.
You can see the accuracies are very, very high. You can see that the accuracy is very nice. The scores are good.
Sure. Reda.
Yeah.
VGG, it has 2 dense layer. The last 2 layers are dense, no?
Yes. Well, I'm not sure.
We should stop them or no?
I'm not sure if this version of the VGG that we have, generally what people share, they don't share the dense layers. They share their CNN layers. But I don't know. Here we are freezing everything. So I'm not sure if this version of the VGG has the dense layers or not. I have to have a look at it and see.
Summary. It
I'm not
cannot
sure.
display.
It cannot what? Sorry.
Summary. It doesn't display the.
Yeah, it's because this one is a class of model, but there is probably a way to know. There is probably, I don't have it in memory, but I think there is a way to know internally how it is made. I will try to have a look at it. If you can find it, that would be great. To see if we can internally find the architecture of this layer.
I will search for it.
Yeah, I think there is a possibility. So here we got like 15 epochs, but we are getting super high accuracies here. And very quickly from like third, we are at 90% at the third epoch. This was very weird, like while accuracy was 100% here. It's probably because the dataset is not that big for testing. But this dataset is not really a good one. Because when we reach 100% at the beginning with testing, it means that we don't have a lot of, it's too good to be true actually. But we quickly here got high scores. So now we are, yeah, we finished. So we got 95%, 96%. And the training was fairly fast compared to last time. Do you agree, guys, with me?
Yes.
I think last time we did use the higher number of steps. But here the network is much bigger. VGG16 with 16 layers. Last time we had like 3-4 layers plus another layer. So it's so if we don't count the 3 other layers, so we have at least here 14 layers. Last time we had like just like 3-4 layers, and the chain was very fast and the results were impressively good. So this is how transfer learning works. You take the model, you download it, and you stack it with other layers. One thing that I want to mention is that this VGG16 was trained with a certain size of the image. The input is fixed. The size of the input is always fixed for a CNN. We can't like train a CNN with an image that is like 200 by 200 and give it an image that is bigger, for example. We have to resize it because the number of inputs is fixed. So we have to resize it. And also, sometimes the image is encoded in a way, for example, RGB, where each value is between 0 and 256. This is the typical values for RGBs. Sometimes they are floats. They are coded between 0 and 1. So we don't know exactly how it was trained. So if it was trained with values, input values between 0 and 256, and you train them with images that are between 0 and 1, then you will get poor results. So this is why we call here process input. Processing, like we pre-process a function, and this comes with VGG. So we are importing it in here. From Keras, it is available. So when Keras loads the images, we tell it here with this line, apply this function to every image. It makes it in the same format as the one that were used by VGG16. So we won't have problems. They will be encoded in the same way, in size, and especially in these values, whether they were between 0 and 256 or between 0 and 1, depending on that. So we have to transform them to make them similar. Does it make sense for you guys? Yusuf, does it make sense for you?
Yes, it's okay. Not really 100%, but
yes. Suppose that just to make it simple. Suppose you have a neuron, a network, a single neuron here. It is connected to a whole image, a big image, a full connected neuron. This image is encoded by values between 0 and 256. So 0 means black, 256 means white, and in between it means gray. Then you have another image. So you train this neuron, it's achieving good accuracy results, say 95%, for example. It's almost impossible for a single neuron to do that with an image, but let's assume it is possible. Then you get an image, the same size, or a different size. Say this one is 200 by 200. This image is 300 by 300. How many weights this neuron has? How many weights? 200 by 200 plus 1.
Yes.
Yes.
But if this one is bigger, then some portion of this image will not be connected to here. We will lose something. It can be connected only to this. This has 200 by 200 inputs. So this one needs to be of the same size. Otherwise, we cannot apply it here. Does it make sense?
Yes, yeah.
Okay. Then again, so we resize it. We make it 200 by 200. But if it is encoded of values between 0 and 1, 0 means black, 1 means white, and in between gray. So when we push it here, it will be, this neuron will take it as if it is almost all black. Yes or no? Because all the values
Yes.
are between 0 and 1. And
Yeah.
this, 0 point something will look like close to black. So this neuron will not do a good job. It will do a poor job. Yes, Yusuf?
Yes, yeah.
Yeah, it's like I'm giving you an exercise with different, like you know how to solve an exercise by using liters, and then I give you like cube meters things like values. So you're probably not going to have good results. You will get results based on your previous training. You don't know like meter cube or these things. So we need to make things the same. Fortunately, VGG16, it has these parameters, and we don't need to know them. So they give us this function to transform images, and we just call it here. And it automatically makes the image the same as the ones used by VGG16. And that way we won't have this problem. So we need the pre-processing function. It is called, when you have transfer learning, you always need a pre-processing function that you apply and to transform the data to a similar data that were used originally, similar format. Does it make sense now, Yusuf?
Yeah, more clear now, yes.
Amal, Miriam, guys?
Yes. Yeah. Thank you.
Perfect.
Yes.
So let's stop here. I think that's too much for you guys for a session. Thank you for your focus.
Thanks,
and
Red.
see you next time.
Thank you.